I just wanted to go over this problem again with some graphics um, and just to show you how far off we were because of that initial slope. And with this I wanted to plot it using a surface or a slope field. So this is the differential equation written as a slope field using this graphing calculator program. And it's probably hard to see, but let's see if I can change the color a little bit so you can see the slope fields. And specifically at 1, if we look at 1, you can see that the slope here is pretty steep, and then we would follow this until we get to 0.5, and then by the time we follow it we'd be down below the x-axis, so it'll be negative. I did compute the actual differential equation, and the actual differential equation looks like this. Well, this is for general differential equation, but if we change the value of c, you get the family of curves. And you see there's a lot of movement to the left of, say, this number 1.8 or 2 as I let my c go from, in this case, from -3 to 3, and there's not much movement that goes on beyond that. And I can see that happening because we have an exponential function here. We have a sine and cosine, but this exponential function kind of steadies the graph as you go further along. And so it has an asymptote at 0, and because it's an exponential function, it actually settles down rather quickly. So we want our point to go through the point, we want our graph to go through the point 0, 1, and I think that's going to be close to a c of 1.08. Turns out that the actual c value that we want is 11 over 10. So why don't I just put 11 over 10 there, and we can see that we're going to be passing through that point. So what I'm going to do is I'm going to use Euler's method and go through this process step by step by finding tangent lines, and then we'll see how that works out. So I'm going to gray this out or make it lighter, and then I'm going to make this solution curve lighter as well. And I'm going to start with a point 0, 1, which is where our point begins. Now, according to the algorithm, what we want to do is we want to come up with an equation of a line that goes through 0, 1, and that has the a slope given by this differential equation. Dy dx is equal to sine x minus 3y. And so according to our formula, our y is equal to our y1. Maybe I'll just denote it as y1 right now, or y0, sorry, our first one, y0 is equal to, let's try that again. So y1 is equal to y0 plus the function xy. Well, it's kind of hard to do it here as a text file, so I'm just gonna write down the actual function, and the function is well, we have h and we have the slope. So the slope is the actual function, so that's the sine of x. That's x0, by the way, minus 3y0, and I'm going to change these values here, times the step h. But if I want to come up with a line, I'm going to say x minus x naught, which x naught is equal to 0. So that's my, oops, x naught. So this is the equation of the line that I want to make up, and what I'm going to do is wherever I see a y sub 0, I'm going to put a 1 in. Wherever I see an x sub 0, I'm going to put a 0, because those are my x and y values. So let's try that. This is going to be 1, This is going to be times 1. This is going to be 0. And this is going to be 0. Okay? So if I draw that, I want to get this line. This is the equation of the line that's tangent to the curve that we don't know, but we know the slope field, so we know that this is the direction that we're going. And we're starting from this point 1 comma or 0 comma 1. Now if I follow this down, I'm going to need to zoom out a little bit. I want to follow this down to 0.5, and so I want to get to this point right here, and you see that this is x is 0.5 and y is negative 0.5. So this is so steep that my graph actually went negative when the actual solution curve does not go negative. So that steepness and the big step size kind of brought us down below. So I am interested in keeping this graph, but I want to stop at a particular point. So let me do this in a couple of steps to show you the graphics behind it. I want to stop at the point where x is equal to 0.5 and then y is equal to whatever this function is. So this is the line that I have, and I want to stop at this point 0.5 when x is equal to 0.5. So I'm going to make it easy for myself and just use the equation of the line, and I'm going to put 0.5 in for x, and that's going to give me that point where I'm supposed to stop. Okay, now this line being this long is a little confusing, so I'm going to also cut my line up a little bit. So I'm going to make it go from 0, x is equal to 0 to 0.5. So now I'm just looking at this line segment. So this is a piece of the line that's going to mimic my solution. Now from here I want to create another line using the slope. So the slope here, if you look at this arrow, it's kind of small. Let's see if we can zoom in a little bit. If you look at that arrow, the arrow is clearly pointing up, so that's going to be my next direction that I'm going to take. But that slope is going to be given by this function again. But this time, that's the slope at 0.5 comma whatever this number was. Oh, this number was negative 0.5. So I wanna draw another line from this point. So let me zoom back out. And by the way, this has a nice way to simplify our expressions. I can just ask it to simplify, and then I get 0.5, and so I still have that line. Alright, so on to creating a new line. I'm going to copy and paste. And I'm going to keep the color red for this. So this time I want to keep an eye on my y values. My y values have to be negative 0.5 now. So the 1 and the 1 that we see here are the ones from the previous step. My new step, I have a different y value of 0.5, so I'm going to change that, negative 0.5. Now likewise my x is also changed. My x is now positive 0.5, so wherever I see my zeros that used to be zeros is going to be positive 0.5. Now of course I want to get this now from 0.5 to 1 because that's our next step. So I'm going to go from 0.5 to 1. So I can see that little piece. So the graph goes down, and then with that slope that puts it up, I'm going to take a step, and then I'm going to go all the way up when x is equal to 1. And so this is going to be my new graph point. Alright. Now I think I want to put that point there, so let's get that point here. This has a point at 1. So remember, this is what we want. We want x is equal to 1 and y is equal to whatever that line is. So let's put a 1 there, and then let's copy the equation of the line without the y here, because that's the y value. And then I want my x to be equal to 1. So I'm going to put 1 in here. And when I do that, I see that point at the end of that line, or that line segment that I had drawn. And this is my my second step. Okay, So I'm going to simplify this again, and so we get this 0.489. Okay, so that's those are the values that we got in class. Now let's keep going. So remember, our steps, we're stealing our values from the previous step, so all the y values here become positive 0.4897. So let's change the y values there. And then my x value is now 1, so this is our x value. We're going to change that into 1. We're going to change that to 1. And this time we're going to go from 1 to 1.5. That's our next step. Oh, we forgot to look at the slope, but the slope looked like it was starting to go down. If you look at these arrows, it's starting to go down. So it was down, up, and then down again. And then we stopped here at 0.5. So what is this point exactly? Well, this point has an x value of 1.5. And then the y value, we'll calculate it by taking our line and by putting 1.5 in for x. So here we are. And we got one more step to get to 2. So let's take that one more step. Oops. Let's try that again. One more step. I'll keep this red. Let's simplify this so we can figure out what the current y value is. It's 0.175879. So that's the current y value. Let's change all the y values here. And then our x value is 1.5. And then this time we want to graph from 1.5 to 2, and this is our last line segment that we're going to consider. So we're over here. Let's actually plot that point, then we'll see our y value. So this is a 2 in for x, and then we want to take our line equation, and in our line equation we'll put 2 in for x. And here we go. This is our last step. And compared to the graph was, if we're following this graph, the graph here looks like it's about 0.316, and then our last evaluation of this looks like it's 0.41. So it's a little high. It's a little high, but that's because our initial step here took us kind of way out of the loop, but it came back a little bit. So if we take smaller steps, we'll probably do a little bit better. And I actually did take some smaller steps. If you guys can take a look at this. Here our blue graph is our actual curve, and with a smaller step of 0.25, we didn't go down as far, and it kept going down, and then it bounced back up, and then we got a little bit closer. So in our last step, if we simplify our last step, we get 0.32, and remember the actual value seemed like it was 0.31, so we got a lot closer. Let's get rid of the field so we can see it a little bit better. So with our smaller step size, we're going to get to it a lot closer than we did before. But then the sacrifice is, of course, there's more work to do and more algorithms. If you're doing this by hand, that's a little too much. If you're doing a computer, you can probably get to there a lot quicker. Instead of step sizes of 0.5, we can take a step size of 0.1, and it will be a lot tighter to the graph. Okay, so that's our graphical viewing of our problem that we did in class. Let's take a look at that problem again. We got 0.4108 with our solution, and we got 0.4108 when we did it graphically. Alright, I hope that illuminates things a little bit, at least you can visualize it. Okay, good luck.